Here we are at last, after a 3-decade-long journey. What lies beneath my feet, well, 350 meters to be exact, is the result of a process that started in the mid-1980s. South Africa's third pumped storage scheme, the largest in Africa and a solution to a country's power needs. In the late 2000s, South Africa was gripped by an energy crisis. Electricity demand had outgrown supply, and Eskom was facing public outcry. Help, however, was already in the making.
I've been experiencing the pains when Eskom load shed the country, the outcry that is coming as a result of that, and the hope of Eskom and the hope of the people of South Africa is for us to deliver as a group capital division. Now that perspective is very clear, but it also gave me an opportunity to start to reflect in terms of what needs to be done for us to deliver. And for us to deliver is to mainly focus on the nuts and bolt. We are in the right track in terms of stabilizing Eskom, eliminate or eradicate load shedding completely, and make sure so that from the revenue point of view, we put more megawatts and we are stable as an organization.
Foreseeing the country's growth and insatiable electricity demand, Eskom chose Ingula from 3 shortlisted sites. Sites with suitable geology to accommodate a pumped storage scheme.
It all started when an identification study was carried out by Eskom in various provinces of South Africa. We identified some 20 schemes. After that particular study, we found that Ingula was the most suited for development first.
The project basically is a pump storage scheme. Well, the main underground works portion of the pump storage scheme comprises of tunnels. 7 of those kilometers are for the carrying of water from the top dam to the bottom dam. And in the middle of that, there is a complex of 2 major caverns. One is called the machine hall, and that houses the generators and the turbines for generating the electricity. The electricity from the generator will then pass through to the transformer hall, where the power is stepped down to such that it can be transmitted in cables that will come out from the underground works and then connect via a switch yard to the power reticulation of South Africa.
The Ingula Pump Storage Scheme is a multidisciplinary engineering project, and by that I mean that it really covers all aspects of engineering. From the civil components on dams, tunnels, concrete works, through to mechanical and electrical components. And then there's the electronics and controls and instrumentation systems that go with it.
Soon Ingula would play a key role in Eskom's capacity expansion program. Eskom was gearing up to add more than 1,300 megawatts to the national grid to use when we need it most.
We will typically generate electricity for your peak demands, and when the requirement is at its lowest, typically over the weekend, we will actually start to pump the water back up the mountain.
A pumped storage scheme is a peaking power station and only produces electricity when demand is high, like in the evening and morning. Ingula is essentially a natural rechargeable battery. During peak energy consumption, water is released from the upper Bedford Dam down through the turbines to generate electricity. It is then released to the lower Bramhoek Dam, thus depleting the battery. Then, when industry and people don't have any pressing electricity demands, the process is reversed. excess electricity from the grid is used to pump water back to the top dam, recharging the battery.
We all have need of this battery. It serves our daily lives and drives progress of society. Everyone in this area was about to become part of that progress.
The area around the proposed building site has witnessed changes over many epochs. And its rich and diverse history was about to receive another chapter. The San were without a doubt the first people of this land. But the chronicle of this area is much more diverse. And even includes creatures from prehistory. Geologically, this land forms part of the Karoo Basin and was once the center of one vast continent with a life-giving heart. To this day, the water that flows from this life-giving heart gives Ingula its name.
Ingula is the Zulu word that describes the froth on top of fresh milk, and was derived from the crystal clear waters of a nearby river with the same name. The name might have come as a comment that the water satisfied much like soothing milk.
Just so, Ingula is an elixir to soothe the country's growing thirst for electricity. It's hard to believe that such a tonic is almost 90% hidden inside the mountain. Great progress is often born from disruption, and soon the landscape was buzzing with earth-moving equipment. Excavation of exploratory tunnels began in late 2007, and the snowball of industry soon accelerated.
Follow me as we investigate what it took to build Ingula.
In total, nearly 16 kilometers of tunnels and 8 kilometers of waterways were dug. $3 million cubic meters of rock was removed, and 7.6 million kilometers of reinforcing steel bolsters this underground marvel. Where to start? Vertical faces are cut into the unspoiled landscape down to bedrock.
Opposite us here is our jumbo, which is the drill rig. Once the surveyor has marked out the face, the jumbo will come in, position itself, and then we have a drill pattern which is punched into the computer, and then we drill the 3 meter or 4 meter holes, and from there it will move out and the charging will be done.
Holes for explosive charges are drilled, and soon these vertical faces become tunnels by controlled explosion.
What's happening here today is we're going to be holing through the Telrace tunnel. This is 2.3 kilometers of tunnel. The diameter at the moment is something like 11 meter diameter in the tunnel. And the amount of tunnel that we're blasting out today is between 4.5 and 5 meters. It's 1 kilometer from either side, and we're roughly meeting in the middle at about 1,100 meters.
Utilizing this drill and blast technique, these exploratory tunnels descend ever deeper into the mountain.
The rock itself has been pulverized into smaller fragments. The fragments are then removed and taken and spoiled. Thereafter, the next part of the process is to support the hole. So we need to support the roof of that hole as well as the side walls. And we support this with various methods, but one of it is rock bolts, cable anchors, and shotcrete. And we use a combination of all three in most cases.
I mean, we're excavating in mud rocks, and that requires that we open up the excavation in a very controlled sequence. And as we open up each portion, then we must install the support.
It's every engineer's dream, really, to work on projects of this nature. And I think that these types of projects don't always sort of come across your desk, particularly in the South African context. We're generally looking internationally to keep our professionals involved in projects like this. So to have this on your own doorstep is certainly, from a personal perspective, is certainly my dream. And I feel very passionately about the sphere of engineering, and certainly hope that the future opportunities will present themselves in the South African context. The challenge as a joint venture going forward would be to, the fact that we've now developed these skills is how do we actually retain them in the South African context, or certainly regionally for that matter. So these are the kind of challenges that we're going to have to deal with in the future to ensure that we keep these engineers based in South Africa but working on international projects.
My name's Karel Stoop. I'm the construction manager. Basically, I'm responsible for all the construction activities on site, which include the civil works. That's the machine cavern, the tail raise, again, the head raise on the top. I think it's one of the best projects to be involved in Eskom right now.
Aided by electronic distance measuring instruments, engineers and workers descend precisely to where they can start to hollow out the main underground works.
Wait.
Points are meticulously plotted and matched to the surface surveys. Gradually, the machine hole is excavated from the ceiling downwards in layers called shelves.
The machine hall has 3 full-width main floors. This is the operating floor, the generator floor, and the turbine floor. In the middle of the machine hall, we have an erection bay. This erection bay is where all the electrical and mechanical equipment is assembled. And once it's assembled, they will be put into position at the various units themselves.
We literally drilled holes into this rock, charged it with explosives, blew it up, and then removed it with ADTs and excavators. And we went the full span of 183 meters and built the ceiling first. And thereafter, we blasted out parts of the floor that we were standing on. And we progressively drilled and blasted at that point in time.
We had probably about 10 drilling jumbos, for instance, drilling the rock to feed in the explosives to blast.
The machine hall forms the heart of the pump storage scheme, and it houses the 4 power units, the main inlet valve, the pump turbine, and the motor and gen.
As soon as we completed the excavation, then we really had to cast the foundations upon which the turbine sits and gradually work our way up, working in close collaboration with the mechanical contractor, the turbine contractor, and we built the machine up in stages.
As excavation progresses, the exploratory tunnels eventually become travel tunnels.
Men, machine, and tons of tunnel spoil is removed to the surface in these tunnels.
The entire underground system was excavated in this manner. Most of the rock that was removed here was sodium-rich mud rock. This sodium oxidizes when exposed to atmosphere for the first time in millions of years, and the rock soon breaks down. To dissipate the stress of the mountain above, rebar mesh and long rock balls serve to make for a very strong man-made cave, while shotcrete serves to keep the mud rock from oxidizing and crumbling.
The transformer hall is the second of two large carvings. At 18 meters wide, 22 meters deep, and 175 meters long, it was a formidable building challenge. Here is where the 4 generator transformers do their work.
These caverns both have multiple levels to accommodate the equipment and support systems. Before these levels can be built, a blank canvas has to be cleared for the civil works to be built upon.
Linking the transformer and machine halls are 4 bus bar tunnels.
These tunnels house a type of electrical junction in which all incoming and outgoing electrical current meets. Concurrent to the main caverns, workers kept on digging at many other sites of the Ingula pump storage scheme. 2 water reservoirs were also taking shape on the surface. The lower Bromhoek Dam, which would become the main water catchment, and the top Bedford Dam that would store Ingula's potential energy.
Right now we're at what's known as the Bromhoek Dam, which is the lower of the 2 dams on the scheme. Designers investigated 3 options for building the dam, one where it is now in the narrowest part of the valley, and then 2 sites further upstream, slightly upstream. The advantage of the upstream sites is that the foundation conditions are a lot better, but the disadvantage is that the valley is wider there, so just to go 50 meters upstream would double the size of the wall. So it was a cost exercise to see which was the most economical solution. And the decision was taken to build the dam in the narrow part of the valley, take the risk on the poor foundation conditions, and we've had to do a lot of significant amount of additional drilling and grouting, extra excavation, concreting to handle the foundations, but we're now comfortable that we've achieved closure of the grout curtain.
At the top of the Little Drakensberg escarpment sits Ingula's other major dam project. The Bedford Dam stores Ingula's potential energy. Its water is held back with tons of rock and a thin sheet of concrete.
861,000 cubic meters of rock infill acts as the weight behind its 830-meter concrete face.
We're on the upstream side of the Bedford Dam, which is, as you can see, a concrete-faced rock-filled dam, and we're looking at the concrete face at the moment. This is a completely different construction. So the wall is built out of rock, which we've quarried on-site, and the waterproofing is done by a fairly thin concrete membrane on the front face of the dam. Full supply level is at the base of the parapet wall. So it's really just on the shadow line between the slope and the vertical piece. Looking at the downstream face of the wall now, which is where you can see the rock fill exposed. It's not covered with concrete. And the outer layer, which is what we can see, is very carefully placed riprap. Quite a skilled operation with an excavator, and the operator takes each rock and puts them in one by one until he's got that pleasing visual appearance that you see there.
At both abutments, a clay core prevents water from seeping through the wall.
Although this type of dam is not unique, the Bedford Dam Wall has won numerous awards for its innovative and complex engineering.
It was precisely during the early stages of excavation for the Bedford Dam Wall Foundation that Ingula served up a most welcome surprise.
While digging and blasting down to bedrock, workers laid eyes on bones that had not seen the light of day in 250 million years.
Right across at the base of the dam wall, we were exactly in the death zone, and we encountered fossils over that whole area down at the bottom of the excavation there.
Workers immediately notified Eskom of the strange rocks making their appearance. Plans to preserve these prehistoric remains were set in motion. Specialists from the National Museum in Bloemfontein were soon on the scene, excited at the amount and quality of the fossils. As the fossils were methodically exposed, their identity slowly came to light. Mammal-like reptiles that lived and died in an era preceding dinosaurs by 200 million years.
Although we don't know what this specific animal is at the moment, it needs to be prepared, they need to clean it out. But what we know is that these things had some vicious teeth. There you can see one that is glue. I put some glue on so it shines. There's one that you can see is a bit more in its natural form. And there's one with just a little bit of glue on it. But you can see the size of the teeth of this animal. Now what Joel and Sam is doing, they're just preparing some of these blocks to see what is the quality and the content of the fossil material inside these. We've discovered some complete bodies already. We discovered some places where you actually have one bone only, some ribs. So this whole deposit of rock that you see lying here was carted here from the excavation site. Every one of these rocks have actually been marked, and we know which one fit onto the other one. So if we find a body or parts of a body in one of them, we know which other one to look for and then fit the two pieces together.
Fossils of ancient plants, Gorgonopsin, Dicynodon, and many more soon unfurled a picture of their final hours. Specimens were thoroughly catalogued, preserved, and sent to the National Museum in Bloemfontein. Here, the bones will be removed from the surrounding rock, identified, and preserved.
Once a fossil is discovered, we estimate what it's going to take to get the fossil out of the ground. If it's very fragile, we need to wrap it and protect it in some kind of casing. With paleontologists, we use plaster of Paris mostly. So we will dig an area around the fossil and cover it with plaster of Paris to form a protective jacket. Once it is dry, we will hack more around the fossil and turn it over and plaster the other side as well, so that the fossil is completely encased in protective plaster of Paris. We then transport the fossil back to, in our case, the museum, where we then remove the plaster of Paris jacket until the fossil is exposed.
The discovery of an ancient fossil bed was very exciting for everyone. However, it was very important to keep the bigger picture in mind. The end goal, after all, wasn't paleontology, but engineering.
Construction on the two dam sites was started in 2007.
Machinery, engineers, and about 4,500 workers now set to work.
Expanding and shaping the farmlands and valleys into two dams. To generate electricity, these two dams need a relative distance and elevation from each other. This distance and height disparity create the massive speed and pressure needed to spin the turbines. Water from the Bedford Dam, having done its work, comes to rest in the Bramhoek Dam. It holds 33 million cubic meters of water and is the main water catchment of the scheme. Bramhoek Dam utilizes a dry concrete mix called roller compacted concrete. It needs little form work and no steel reinforcement, making it simple, fast, and an economical way to build. From the tail race outlet structure to the wall itself, massive amounts of cubic meters of concrete was used. The tail race outlet structure and its massive spillway empties into the Bramhoek Dam and was built at the same time as the wall. The concrete at this point needs to be meters thick to prevent the speeding water from destroying it. The Bramhoek Dam site was also the source of a rich seam of dolomite, a valuable commodity on a project that uses millions of tons of rock to produce concrete.
This is our aggregate quarry. We've actually mined this from dolerite rock. It's basically to supply the entire project with concrete aggregate. That's a batch plant that's being used to actually build the dam wall. They have a mixed design for the different strengths of concrete that they actually need to use on the dam wall. So it's basically a fully automated sort of batch plant that produces your concrete on site.
The 2.6 million tons of rock used during construction was quarried from the Bramhoek site and supplied free of charge to contractors for their concrete needs.
What we have here on my left is crusher sand, which is the final product that will be used by the main underground works. We're producing about 1.3 million tons of sand, which is the finest product. It's a -2 millimeters of sand.
The stone from the quarry is first crushed and processed into aggregate of varying sizes. Everything from riprap to crusher sand used for shotcrete was sourced from the Bramhoek quarry. These quarries were flooded during the planned impoundment of Bramhoek in 2011. Unfortunately, the outlet structure flooded prematurely after heavy rain inundated equipment and stopped work in progress. Earth-moving equipment on a barge had to be used to clear the outlet structure of building debris under the water's surface.
You're looking at one smiling engineer, because the biggest risk to this scheme was that we could have had no water when we come to commission if we'd had 3 dry years between now and then. We've been very lucky. We've had an exceptionally wet year, and we're at 95% full. So we've basically filled the dam in one season.
To prevent unsightly holes, all the quarry and borrow pits at both dam sites were excavated under the minimum operating level of the water. Because of the remoteness of the Ingula building site and the fact that most of the civil works took place underground, a necessity of this project was an on-site batching plant. The massive amount of concrete required by such a large building program is made 24 hours a day, 365 days a year, during the peak of building activity. Cement, stone, and other raw materials had to be on hand and available at a minute's notice. A vital partner in quality control and delivery of concrete and aggregate on site is the laboratory. At the on-site lab, testing is done on everything from water quality to aggregate density and concrete strength. To help workers and engineers in the field, tests are done to determine optimal mixed densities and techniques. The aggregate from the quarry eventually makes its way to the on-site batching plant where the concrete is made to order. Because of the exothermic nature of concrete and the distance it needs to travel, ice is made and added to the mix to slow down the setting process. Cement is fickle. As soon as it mixes with water, the chemical process that makes it such a formidable building material is set in motion. There are two ways one could use to delay this hardening. The first technique is to keep the cement in motion. The second technique is to keep the concrete mixture very cold. Ice made on site inhibits the chemical process and gives workers more time to pour the concrete. A fortunate side of this cooling process is that the final concrete mixture is also very strong. The Bedford site yielded more than just prehistoric remains. Cave paintings of eland and leopard adorn the walls of a cave on the eastern border of the site. These treasures were removed and preserved as the cave would be inundated. And as the wall would be built in a sensitive bird area wetland, great care was taken with the environment. Indeed, this adherence to conserving the environment was not just lip service. The Ingula power plant would never have been built if the environment was not protected, nor would the Nature Conservancy have been established if Ingula was never built. Conserving the environment in the area ensures both the license and ability for Eskom to operate. As a small part of the overall conservation plan, both these walls had to be built with environmental release valves. Water has to be released into the downstream systems to what the normal daily flow would be. All this water has to get into the mountain somehow, right? As the earthworks site-wide progressed, workers were burrowing from the top side through the mountain to the machine hall and beyond. Let us take a look at the water's journey. It all starts in the leisurely 800-meter-long approach channel. Built to mimic a natural ravine, it ends in the trash racks of the intake bell mouth. It picks up speed as it flows into the low-pressure head race. For 1,000 meters, it picks up speed and pressure before encountering the surge shafts. The surge shafts descend 200 meters into the mountain from the surface. They serve as shock absorbers, maintaining hydraulic stability during operation. The roller coaster now starts in earnest. From its modest 11-degree incline, the pipes now slope at 24 degrees. At the end of this speedway, it flows at 17.3 meters per second. Pressure here is extreme, and the pipe is made of steel sections as thick as 6 centimeters. These steel sections are manufactured at the top site. Flat steel is shaped into massive cylinders called cans. each can is hefted into the underground works via the surge shafts, lowered into position and welded.
Some cans are also trucked to the bifurcation edit via the main access tunnel.
Water is finally near the generator. The two-head races now bifurcate, each delivering water to 2 machine sets. Because the bifurcations need to withstand massive pressures, there are hundreds of constituent parts were continuously heated to relieve stress while being welded. Now the water gets to work, spinning the turbines of each machine, and is released down the draft tubes.
Into the surge chambers, where the water's energy is diffused again. 4 draft tube gates are housed here.
During emergencies and maintenance shutdowns, these gates isolate the machines from the tail race waters. Having fulfilled its function, water enters the tail race, and 2 outlets become one at the tail race confluence. Advancing ever forward, a tunnel lining machine shapes this massive pipe.
The water is finally out in the open once it passes through the outlet structure.
Now at rest, the water waits to be pumped back during off-peak times.
Our diesel gens, they're built by a company called MTU, actually come out of the Mercedes-Benz stable, MTU. Build these large generators for ships predominantly. It's their target market, but you would also find them in a lot of backup power type situations in our power stations. Quite impressive machines in themselves. They have 16 cylinders. It's a V16 configuration, 4 turbos. So very much like that Bugatti Veyron machine.
Those diesel generators provide a standby power supply. I mean, if the grid goes down, then we've got to maintain the station. And we're in an underground excavation with water seepage is always present in any underground excavation. We've got to keep that under control. So we've got to, if the grid goes down, we have no access to power, then we've got to be able to power up the pumps in the main drainage gallery to get the water out.
They also is the first power we would utilize if we ever blacked out the entire country. So when people talk about a black start, the two 1.8 megawatt diesel engines at Ingula is where we're actually going to restart and kickstart the country back into life.
We need to remember that all this construction was occurring concurrently. Many parts of this underground labyrinth was being burrowed to achieve one end. With a blank canvas cut from the rock, thousands of workers descend into the depths. Soon, civil and mechanical work would start transforming these bare walls.
All these men and women would have to be fed while working underground. Food for the underground works is measured and prepared in hundreds. It is hard work, but eventually everyone on site has 1 meal a day delivered to them.
Well, for the time being, challenges are because to maintain our standards, this is the main challenge. Because we maintain special standards for the expatriates. So everywhere we go, we do the same thing. A day for a meal, Entire site, we need about 200 kilos of chicken for a meal. Beef, about 170. And if it is pork, 180. Where all the rooms are cleaned every day. The linens are changed twice a week, the linen and towels. So all the rooms here, they have separate bathrooms and everything. So we have the room cleaners and the laundry is done every day.
Eskom is wholly committed to the safety of its workforce, and everyone on the Ingula side has to know the 5 life-saving rules of Eskom by heart. These cardinal rules, combined with rigorous training and medical evaluations, ensure that lost time injuries don't cripple the workforce and work.
Absolutely crucial what happens here, because some of the people are not the people that will see a doctor on a regular basis. So for the clinic to be here and to reach across to those people, I think the impact is profound. I think it's amazing what has been happening.
Hard hats, overalls, and steel-toe shoes were to be worn at all times. And everyone that enters the underground works must take possession of a rescue pack and a headlamp from the lamp room. Not even presidents are exempt from wearing the correct personal protective equipment.
Working in construction, one of the most important things is making sure that we don't have accidents. We have to make sure that we're healthy, and this whole team here work towards doing that by making sure that you don't feel sick, so that you can concentrate, that you are treated on time, that you don't feel anxious. And because when all of those things happen, your concentration goes down and accidents can happen. So that is part of what our team here does, is keeping you healthy so that you can work safely and go home in one piece.
Toolbox talks are held to ensure that all workers have a permit to work and understand all the risks as well as their responsibilities for the day. Safety and quality control officers roam the site checking that everyone is safe and that work is up to standard.
To make the presence of safety felt at the workplace, we actually build good relationships with contractor supervisors, with contractor teams, and of course we have to know the activities, the programs, and we also have to know the risks related to the activities, and to actually communicate our minimum standards to them so that we can get them on par with what we require. And if you have achieved that, you can be very successful because you can change the contract and its workplace culture. And behavior and culture in the end is one of the most important aspects in success of safety.
Because of Ingula's ability to jumpstart South Africa's electricity network, it is designated as a national key point. For this reason, security at every entrance was tightly monitored from the very beginning. This commitment to security will continue for the entire working life of Ingula.
The main aim of security measures and control at Ingula is to make people feel safe when they visit Ingula, for them not to feel that they can lose equipment or that they're entering a safe area, and that everything is under control with regards to security measures implemented at Ingula.
Many parts of a complicated puzzle have to be fitted together exactly to bring a generator like this to life. In these early stages, 2 massive cranes are installed. The draft tubes and spiral casings of each machine set are then lowered and encased in concrete. Formwork for the levels are built, and the octagonal barrels that would receive the mechanical leviathans are cast.
Let's look at all the components in more detail. This is one of 4 main intake valves. These valves are gatekeepers of each reversible pump turbine. All said, these valves need to be big and tough enough to hold back the staggering 42,000-ton weight of water on the head race side of it.
That particular valve, the casting of it was done in China, and because we identified it as being critical, we made sure that we had metallurgical engineers that went to check out the casting. The reason we knew that was because China can produce very good quality and it could produce bad. We wanted to make sure that our quality was excellent. So once this was cast, a lot of the machining was done in Korea, and then after that it went to Pennsylvania in Voith to be finally machined and assembled. And at that particular time, there was a factory acceptance test done. The engineers, our South African engineers, designers went there, as well as my inspector.
The MIVs were transported via rail to the harbour from York, United States. From there it was sea freighted to South Africa and road transported to Ingula site.
Each of the 4 main inlet valves are delivered to Richards Bay Harbour and take weeks to travel to site. They are then transported into the underground works, ready to be lowered into place. The MIVs are installed on their pedestals, welded to the penstocks, and attached to the servo arms. This servo and arm will open and close the MIV in under 40 seconds during an emergency.
We live in an imperfect world, but this valve has got to be perfect. There is no leeway for anything on this valve. If there is, it will not function properly and we would have a problem. So the tolerances that we have on this valve, one could say, are virtually down to 0.
When the water from the Bedford Dam rushes through the MIV, it next encounters the spiral casing. Shaped like a nautilus shell, it tapers gradually to keep pressure unchanged, even as the water loses energy and speed. Each spiral casing was built off-site and delivered in 2 sections. These sections are then assembled underground and lowered on top of the draft tubes. The water now rushes through the spiral casing and wicket gates. The 19 wicket gates and spiral casing not only control water, but also control the angle at which water interacts with the impeller.
The water can now put its great momentum and pressure to work. The 72-ton impeller is fitted precisely inside the spiral casing. These impellers are the workhorses and critical energy transfer link between the water and the rotor generator.
The 3 spinning components of the generator are held aloft by the lower bracket. The entire 530 tons of rotor, shafts, and turbine impeller spin on an oil-lubricated thrust bearing housed in the lower bracket structure. So, how does all this water, these massive forces, pressures, and all the spinning machinery turn into electricity? A static component called the stator and an active turning component called the rotor interact with each other to generate electricity. Because Ingula's machines are reversible, electricity can be generated, or the process reversed to pump water back. The stator's electromagnet is stacked from individual sheets over months. The filled coil windings are added last. Both the 265-ton cranes have to be tethered electrically and mechanically to lift the giant stators. Also stacked from individual plates and fitted with 14 magnetic poles, the rotor is the spinning part of the generator. The rotor is lifted into its companion stator. During generation, the movement of the rotor's magnetic force, caused by the spinning impeller, induces an electric current into the stator. This current is transmitted through the bus bars and transformer to the national grid. During pumping, this process reverses using excess electricity to pump water back to the top dam. When each machine is finally assembled, it undergoes rigorous system checks and tests, and is ultimately ready to be commissioned. Which all leads up to Ingula's first pumping event. Before electric power can be generated, Bedford Dam needs its potential delivered to it. When Ingula's reversible pump turbines pump water up to the Bedford Dam for the first time, something special happens. Water from the Tugela watershed and water from the Top Velge watershed unite the Indian and Atlantic Ocean through the underground waterways. This potential is then put to use to generate Ingula's first ever outbound current. When the generator, national grid, and turbine frequencies match precisely, they are coupled. This event is called first synchronization and is a very special event in any new power station. Once all 4 units have been synced and commissioned, they are handed over to the national grid for operation. Electricity now flows freely to our homes, thanks to the enormous power of water. While work underground was reaching a fever pitch and deadlines were looming, another form of construction was taking place on the surface. Excavation above ground had taken a toll on the natural surroundings. Eskom, however, had anticipated this, and there were plans already in place for nature's reconstruction. During the planning stages of Ingula, concerns were raised by interested parties of what impact construction would have on the environment. All this was here before Ingula. All this beauty had to be preserved.
We really went out of our way when we designed the dams to accommodate nature. You look at the bird cliffs that were created at the top site. You look at the Eskom bought 8,000 additional hectares. So it's possible to get a country growing economically as well, but also to look after nature.
An environmental impact assessment found that the site was located in a very sensitive area. There are not only 3 unique habitats here, but also countless species that call these habitats home. Wetlands within the construction area were a thorny issue. The Upper Escarpment wetland, where the Bedford Dam was to be built, is a sensitive and vulnerable biosphere. Disruption or destruction of these natural filters could not occur during construction.
We need to ensure that our conservation area is managed correctly. And of course, all the construction that's happening now has a direct impact on that conservation in the longer term. Now that we are here, we're able to bring those under some type of level of control and hopefully over time increase the conservation value of this area for the benefit of everyone, not only Eskom, of course, but the local community and of course nationally throughout Southern Africa. Look, I think there's 3 features here that are really important. Of course, the wetlands which are critical to our long-term sustainability. We've gone through a level of high rainfall, and the wetlands are our bank. High altitude grasslands are not very conserved as such in South Africa. They have been historically quite badly abused. There's a big idea when one realizes that the grasslands are probably our second most diverse area or ecosystem in Southern Africa after the fynbos. Now, other system, of course, that we have is the escarpment forests, which have got tremendous diversity as well, and we will be having a look at those. So really all 3 of those together come to create a pretty unique ecological system, which has, of course, sustainability perspectives in that it has social benefits and that it does support farming at the moment. It also supports environmental issues. And of course, in the long term, it will have an economic value to the people in this district as well. What we need to ensure is in the longer term that the water flowing into the wetland does not cause scouring, does not cause any impacts on the wetland as such. We need to ensure that there is a set amount of water released into the wetlands at all times. And we have a big stilling basin that has been built at the bottom, water will flow into that stilling basin and will then seep into the wetlands on a continual basis, so that there will be no impact on the wetlands at all.
The construction footprints were predetermined, and it was all aligned with previously disturbed areas. We tried to minimize our impact on the pristine areas, the grassland areas. All of the wattle areas, we've tried to stick around those areas that are prone to disturbance.
The land in and around Ingula hosts hundreds of bird, mammal, reptile, and amphibian species, as well as critically endangered animals. To protect this diversity, an additional 8,000 hectares of land was procured and rehabilitated. Throughout the construction process, environmental officers worked ceaselessly, cataloging, monitoring, and making sure the fauna and flora here thrived. The beautiful fauna and flora here is not the only reason for conservation. To protect this pristine landscape also affords Eskom the legal right to operate a pump storage scheme and to use the water here for that purpose. It is clear from satellite imagery that conservation has had a positive impact on these old pastures. Soon, this will all be a nature reserve where people can come and enjoy its beauty, hardly aware of the powerhouse under their feet. Indeed, access to the public will be encouraged and everyone can find their unique connection with nature in the safe bounds of this national key point. The legacy of the Ingula Nature Reserve will far outlive that of the Ingula Pump Storage Scheme. Long after the pumps stop working and the electricity stops flowing from the underground powerhouse, animals and people will still enjoy this inheritance. Building on such a massive scale is bound to have an impact on the landscape. To mitigate this damage, Eskom uses its stockpiled topsoil to rehabilitate the landscape. Affected areas are covered with tunnel spoil, clay and topsoil, landscaped to match the surrounds, and then hydroseeded. Hydroseed is a liquid mulch consisting of several types of grass seeds, fertilizer, and pesticides. This hydroseed is sprayed over the topsoil and rapidly takes root. Within days, the slopes are erosion-proof.
Ingula is of course a fantastically exciting project to be part of. It's definitely the largest pump storage scheme in Africa. So to be part of something, the actual construction of something like this is truly fantastic and unique. And of course the visitor center will be here for the life of the station, which is at least 40 to 70 years.
The ecosystem services that are supplied by the reserve are beneficial to the area and station. Water supply from wetlands and the soil stability resulting from appropriate management strategies will ensure the station can operate with sufficient water and functioning dams for the foreseeable future.
Showcases how big projects can be conducted while still maintaining high focus in terms of nature conservation, where there is a common approach between different organizations, NGOs having different interests, and how parties can come together and have a common focus in terms of how we can produce power that's required for the grid, whilst at the same time maintaining an area that has a very high conservation value.
The area will actually be controlled by Eskom conservationists. They will ensure biodiversity. So the main reason for actually this power station is to actually generate electricity, but at the same time we've gained largely by actually converting this area into a nature reserve.
So, besides the obvious benefits to the electricity consumer and the environment, who else gains from this project? Eskom knows the importance of investing in its community and people. At the height of construction, thousands of people from the local community were directly employed. However, jobs were not the only dire need here. Eskom saw the pressing socio-economic issues of the local community surrounding Ingula. Unemployment, illiteracy, and lacking healthcare were but a few of the social ills. The literacy and education of young and old became a priority.
We've got 4 pillars in terms of our corporate social responsibilities. We look at education, we look at health, we look at poverty alleviation, we also look at skills development. And lastly is, of course, relocations and resettlements, where Eskom, Ingula, has taken a different view, wherein families who were within construction footprint had to be resettled or relocated. Emerging contractors, for the first time, are being trained. So all the emerging suppliers and small enterprises, SMMEs, and broad-based economic development projects, for the first time, they will have someone, a responsible corporate citizen, funding this and making sure they are trained on how to run their business efficiently and in a sustainable manner. So this won't only benefit Eskom in terms of possible suppliers in the future, but they can do business with everyone and anyone in future. So this is a legacy. And we are also, in terms of our initiatives to provide bicycles to schools, because you have for the first time learners who used to travel 10 to 20 kilometers to school. For the first time, they are able to cut this distance and not only exercise at the same time while they're going to school, but they get to enjoy riding a bicycle. This is empowering. And we are also planning to ensure through our partners and our stakeholders that we can teach these learners who've got these bicycles to assemble and disassemble and fix their own bicycles. This is a magnificent initiative that will train kids to be innovative and think broadly and see the world differently. We're changing the social fabric and changing the landscape of our social community.
Schools that were in dire need of upgrades and maintenance were identified and the wheels of progress were set in motion. Eskom and the Department of Health launched a mobile health clinic initiative. The Bophelong bus and the Fellow Pepper train travel a circuit of schools and remote communities, offering free health care to all.
We understood very well through our studies and our analysis that we are going to areas that are far-flung, rural areas that have no basic services in terms of clinics and all other services. So the mobile unit will primarily be targeting primary school learners and ensuring that it goes to the far-flung areas and ensure this minimum of 20,000 primary school learners do have access to an optometrist, a nurse, and a dentist.
It is hard to believe. Where I am standing now was once one solid rock. Imagination, innovation, and hard work hollowed this mountain out to accommodate the heart of the Ingula pumped storage scheme.
So, let's recap. Right here in the Little Drakensberg Mountains is a power station. It utilizes water, relieves electricity demand, and takes care of its people and environment. It's proof that heavy industry can not only create man-made structures, but also sustainable conservation areas of international significance.